Welcome back. So in the last lecture, we derived the potential flow vector field V, which is the gradient of a scalar potential phi that satisfies Laplace's equation. So in some sense, we actually derived Laplace's equation as the partial differential equation needed to find a suitable potential function phi, so that if you take its gradient, you get a vector field that is steady, incompressible, and irrotational. So it doesn't change in time, it has no divergence, and it has no curl everywhere in space. And so today we're going to zoom in a little bit more and look at what are some of the properties of these potential flows, and what are some of the properties of Laplace's equation. So this is one of the most fundamental PDEs in all of physics, and the resulting potential flow can be used to describe a lot of phenomena in fluid flow physics. Okay, so I'm going to jump right in. And then I'm also going to give a couple of examples. We're actually going to use this complex potential function to derive some potential flows. So the first thing I want to do is essentially just describe some of the properties of what happens in one of these potential flows. So imagine that I have a fluid flow vector field, and we're going to call this V, our vector field, some unsteady flow field V. And imagine that we have some closed curve C. This is just an orbit that we kind of make up. This is kind of like a control volume that we're putting, we're just placing this in the flow, and we're saying what happens inside and outside and on the boundary of this curve. We'll call this curve C. Good. And then one last thing I'll do to set up this problem is at every point we're going to establish a tangent and a normal vector. So we're going to say that the normal vector is n bar, and the tangent vector is a little u bar. Good. Now, a potential flow, a vector field V that is steady, incompressible, and irrotational, i.e. that is the gradient of a potential solution of Laplace's equation, has two really important properties on any closed curve C in 2 dimension. The first property is that if I take a contour integral around C of my vector field V dotted in this kind of tangential u direction, integrated across every little segment of this contour. So I'm literally taking my vector field and I'm seeing how much component of it is in this, this tangential direction u, and I integrate that around the contour. We know that this is going to be equal to 0 because of Stokes' theorem. So by Stokes' theorem, this says that we have this contour integral is equal to a surface integral inside of C, so kind of a surface integral inside C of the curl of my vector field V times every little area element. And again, because we know that this is an irrotational flow by construction, this curl is 0 everywhere. And what this tells us is that if I take my velocity component of my velocity field, dot it into the u direction, and I integrate it around any closed curve C, it has to equal 0. What that means is that there is 0 net circulation. There is 0 net circulation or vorticity around C. And that's for all closed curve C. So this is one really, really useful property of potential flows. Similarly, we can write down a similar property of the divergence of the vector field. So let's write that one down. I'll do this one in orange. And so what we have here is that the contour integral around C of V dotted now into the normal direction, again integrated on every little segment around this contour. So we're again integrating around this contour, but now we're taking the component of V that's pointing normal to the contour. And when we integrate that around, we find similarly by Gauss's divergence theorem that now we similarly have a volume integral inside C of the divergence of V. Times every little area element. And again, by construction, we know that this is an incompressible field, and so the divergence is 0 everywhere. And so we know that there is no net component of v integrated on the surface. And this was that flux integral that we had been looking at before, where we integrated kind of the component of v that's carrying you out through the normal direction of the surface, integrated on the whole surface of the flow field. So this essentially is a statement that there is zero net flux through the contour. So this is zero net flux across C. Okay, so these are two extremely useful properties. Now, you might think that this is a little bit different than the formulation of Gauss's divergence theorem I derived a few lectures ago, where in that case this was a surface integral and this was a volume integral. But the same exact idea applies in 2 dimensions now, where the flux is the integral of my vector field in the normal direction around some closed contour, and kind of the sum of all of the divergences inside is now a surface integral. So this is still Gauss's divergence theorem. This is still Stokes's or Green's theorem in 2D. And so essentially by construction, our potential flow has these very, very nice properties that around any closed contour you can draw in your flow field. Again, imagine this is like the Gulf of Mexico flow, and you pick any closed loop you like. There will be zero net circulation around C and zero net mass flux across C if you have a potential flow solution, if the fluid flow is truly a potential flow that satisfies these conditions here. So I think that's really, really neat. Okay, now what I want to do is actually give you some examples of a potential flow and show you, kind of draw the vector field, analyze the potential flow, show that it's incompressible and irrotational for some of these complex potentials. Okay, so we've talked about what potential flow is, how it relates to Laplace's equation. And in the last lecture, I showed you that if you have an analytic complex function phi of z, this could be something like z squared, z to the third, z to the fourth, cosine z, sine z, e to the z, in terms of some complex variable x plus iy, where I is the square root of -1, the imaginary number, then for any of these analytic complex functions, if you look at the real part and the imaginary part of those functions, they have to satisfy something called the Cauchy-Riemann conditions for this to be analytic. And those Cauchy-Riemann conditions essentially guarantee that the real part, phi, and the imaginary part, psi, are both solutions of Laplace's equation. These are both kind of these harmonic functions that satisfy Laplace's equation. And these can be used as potentials. Can be used as a potential for potential flows. So any analytic function, if you take its real part, and then you take the gradient of that function, that will give you a potential flow, guaranteed. And this is a cornerstone result in complex analysis, one of the most important results in complex number theory. And that's probably why a lot of departments still have complex analysis in part of their core engineering math sequence. Even though it might seem kind of esoteric, it can be really useful to find solutions of Laplace's equation. One of the most useful reasons we study complex analysis. Okay, so we're actually going to do this for z squared. And maybe before I do that, I will point out here that our flow v1 and v2, which is the gradient of phi, I'm just going to write this out as partial phi partial x and partial phi partial y. That is what that vector field equals. Okay, that is my potential flow vector field. And I'll also point out you can get the exact same, these functions phi and psi they're related to each other. They're not completely independent because they're the real and imaginary part of an analytic function z. And so this vector field can also be derived through the stream function as partial psi partial y and minus partial psi partial x. Now this is just, usually I work with the potential function. I am more comfortable with this. A lot of people work with the stream function in fluid mechanics. This is a very common representation of fluid flows in fluid mechanics because essentially level sets of psi actually give you these streamlines. The stream function is constant along streamlines of the flow, so that's a very, very useful quantity. And really, really interesting, this actually has the same structure as the Hamiltonian equations of motion, Hamilton's equations. And so in some cases, you can think of the stream function psi as a Hamiltonian energy function. That's just kind of a neat connection that you can draw from. So I'm just going to say sometimes this is a Hamiltonian. OK, good. So we're going to derive this for z squared, and we're going to actually draw the phase portrait and look at properties of this vector field here. So let's actually do that, and maybe I will do that in blue. So z squared, if I have z equals x plus y, so let's just do this. Z squared equals x plus iy squared equals, OK, I'm going to collect all of my real parts and my imaginary parts. So I would have x squared plus I squared, y squared, which is minus y squared. Those are the two real parts. And then I'll have plus 2 ixy. And what I'm actually going to do, I'm going to move my imaginary out front so I can keep track of it a little bit better. So this is plus I 2xy. OK, good. This is my potential function phi. This is literally my potential function. And this is my stream function. Good. And so now what we're going to do is this z squared, this potential function phi, or this stream function psi, actually establishes a vector field v. So that's what we're going to do. So we're going to say that v equals partial phi partial x. So partial phi partial x is just 2x. And partial phi partial y is minus 2y. Now you can verify that you can also get it from the stream function. If I take partial psi partial y, I have 2x. And if I take minus partial psi partial x, I have minus 2y. So you can get this vector field either from the potential flow or from the stream function. Those both work. And so this is actually my vector field. So the first thing we can do is verify that it's incompressible and irrotational. So that's pretty easy to do if you, I mean, let's just do it, right? So if I look at the divergence of v, it'll be partial of the first term with respect to x plus partial of the second term with respect to y, which is 2 minus 2 equals 0, check. Similarly, we can check that this is irrotational. So we look at the curl of v. And the curl of v is partial the first one with respect to y minus partial the second one with respect to x. The first term doesn't have a function of y, and this is not a function of x, so those are both 0. So 0 plus 0 equals 0, check. So this is incompressible and irrotational. Good. And you could also verify that both of these functions satisfy Laplace's equation. Let's do that. I think I'm just going through the motions of confirming for you that if you have an analytic function and you expand it out in complex variables, the real and imaginary parts are solutions of Laplace's equation and can give you an incompressible irrotational vector field. So just writing this down, what we have is we're going to confirm that the phi function satisfies Laplace's equation, which literally means partial squared phi partial x squared plus partial squared phi partial y squared. Apology, my phis look terrible. That's a phi function. So if I take this function and its second derivative with respect to x, the first derivative is 2x, the next derivative is 2. If I take the same function, the second derivative with respect to y is minus 2. And again, that equals 0. This function satisfies Laplace's equation. It satisfies the second partial derivative sum equals 0. We'll check the stream function satisfies Laplace's equation. So same thing, partial squared psi partial x squared plus partial squared psi partial y squared equals. Now this function, if I take its derivative with respect to x once, I get 2y. And if I take its second derivative with respect to x, it gets 0, because 2y is not a function of x. So this thing, the second derivative of x or y is equal to 0. So again, 0 plus 0 equals 0, check. So what we've done here is we have taken an analytic function, z squared. We've expanded it in the complex variables and collected the real and the imaginary parts. And those real parts and imaginary parts are functions of x and y. And those functions satisfy Laplace's equation. The potential function and the stream function satisfy Laplace's equation. And so if I take the gradient of phi, I get a vector field that is incompressible and irrotational. That's really, really useful. Now, I'm actually going to draw this vector field for you because it looks cool. And I think it will help kind of give you an idea of what's actually happening here. So what we're going to do is we're going to draw this, this vector field. And this vector field is 2x and minus 2y, which means that any point, if I am in just the x direction, if I'm at x equals 1, y equals 0, then this vector is 2, 0. So it kind of is pointing in that direction. And the farther out I get, the faster this arrow goes. And in the negative direction, the arrows are pointing in the negative direction. But if I go in the y direction, if I take a unit step in the y direction, my vector field is 0, minus 2. So it's actually pointing in. And the farther I go, the faster it points in, as you would expect. And so this is how my vector field looks. And if I go a little bit to the left, like at this point 1, 1, then I have a vector that's moving to the right 2 and down 2. And so it will look kind of like this. And I hope I'm actually drawing this right. I think I am. What this ends up looking like is kind of like a saddle function. So this looks like a saddle. Things are smushing down in the y direction and stretching out in the x direction. And so this function, this vector field, is in fact incompressible and irrotational. So if I take a little blob of mass, like let's say I take a little blob of goop here, and I flow it along this vector field. I drop some oil in this vector field and I flow it along. It will stretch out in the x direction. It will get bigger in the x direction, but it gets compressed as much in the y direction. So it ends up getting stretched out in the y direction, in the x direction as it gets smushed in the y direction. And so the total area of this blob is constant as you flow through. That is what we mean by divergence being 0. All closed areas are preserved as you flow it through this field. And similarly, because this is irrotational, this blob doesn't rotate or kind of shear or distort as it flows. It just stretches out, but it doesn't actually go through this solid body rotation. So the orientation of this object remains conserved through this flow. Now, one of the last things I want to show you, and I think this is really important. So let's slow down. I want you to really listen. This is one of the most important kind of ideas in vector calculus, in this whole vector calculus and partial differential equations, is that when we have a PDE, the solution of that PDE often defines a vector field. And then I can take that vector field and I can imagine that I am a particle in that vector field. I can imagine that I am some particle x and y, so that ddt of x and y equals v1 of x and y, v2 of x and y. And so essentially what we get is a differential equation. This vector field can be thought of as an ordinary differential equation for how a particle moves through this fluid flow. So I want to say this again. It's kind of a three-step process. I have a partial differential equation. So I have one, I have a PDE. 2, that gives me a vector field V. And then finally 3, we think about a particle, the ODE. This vector field V is an ordinary differential equation for a particle in the vector field. And this is a really, really important concept that oftentimes, for example, the Navier-Stokes equation is a partial differential equation. The solution of the Navier-Stokes equation is a vector field V. It's not steady and compressible and irrotational. It is unsteady and has, can be compressible and rotating. But it's a vector field V. And then I can think about particles in that vector field, and I can drop particles in that vector field and integrate them along. And so that's kind of a three-step process we use to think about partial differential equations, vector calculus, and flows in general. And so we're actually going to integrate particles through the Navier-Stokes vector field, which is the solution of the Navier-Stokes equation. That's one of the most useful tools we have for visualizing fluid flows, is integrating particles and seeing where they go. You know, in smoke visualizations, in old wind tunnels, you'd put a cigarette or a piece of incense in the wind tunnel, and you'd see where those particles collect. And that tells you a lot about the structure of that flow, looking at where particles collect. When we unfortunately or accidentally drop pollution in the ocean, we can see where it goes, or we can predict where it goes by integrating those particles through the Navier-Stokes vector field, which is the solution of a partial differential equation. Very useful stuff. And you can picture that here. So in this case, I said that this looks like a saddle. It doesn't just look like a saddle, it is a saddle. So if I take this vector field here, I have x dot and y dot equal 2x and minus 2y. And if you like, you can write this in our normal ordinary differential equation form as a matrix, 2, 0, 0, minus 2 times the state vector x and y. And so now you see that this is in fact exactly a saddle point. This there's a fixed point at the origin of this differential equation. This is a linear ODE. It has a fixed point at the origin, and it has an eigenvalue of +2 in the x direction and -2 in the y direction. If I looked at the eigenvectors, the +2 eigenvalue would have an eigenvector in the x direction. The -2 eigenvalue would have an eigenvector in the y direction. And so this, this potential function here, which satisfies Laplace's equation, gives me a potential flow vector field v, where if I drop a particle in that potential flow, it behaves according to this linear saddle point ordinary differential equation. My particles literally are going to do what I expect my saddle points dynamics to do. Okay, so this is what would happen if I integrated a particle along that vector field. And that's a really, really useful perspective. So we're going to, in the future, we're actually going to use this to study more complicated fluid flows, like the ocean gyres is a really common vector field that you can model as a potential flow. So if you look at ocean flows, often there's two big counter-rotating basins that have big circulation, and occasionally over seasons they kind of drift and breathe. And even that very simple model of two counter-rotating vortices that breathe can give you chaotic mixing in the ocean. It's a really cool model system. And it can be modeled, it turns out, using one of these potential flows. So I can essentially build a potential flow in a box that has these two big counter-rotating vortices. So this one moves in this direction, this one moves in this direction. I hope I can draw this. It's a little tricky to get just right. Okay, this one's going this way. I guess this one's going this way, and so on and so forth. Okay, so this is just a big counter-rotating set of vortices. And it turns out that there is an approximate potential flow solution that gives you this kind of counter-rotating ocean gyre. And you can modify it to make these slosh back and forth. And that potential function, actually, I'm going to do it with a stream function. That stream function is just psi of x and y equals sine pi x times sine pi y. And you can verify that that vector field that you get out by taking this partial derivative here satisfies this, this vector field. So v equals, partial psi partial y and minus partial psi partial x. And it turns out that that equals a vector field given by pi sine pi x times cos pi y. And another, the y component of this vector field is minus pi cos pi x times sine pi y. And if you actually, in MATLAB or in Python, start plotting kind of the streamlines, the level sets, or you start plotting this vector field established here, you'll see that this actually creates this counter-rotating ocean gyre. And so this is something I often with my class will code up, and we'll start dropping particles. We'll see where they start stretching and mixing, and we'll actually compute these quantities and compute, drop a blob of particles and see how they stretch and fold. Okay, so big picture summary. Potential flow is a really, really useful subset of vector fields that are steady, incompressible, and irrotational. They are obtained by taking the gradient of a potential function that satisfies Laplace's equation, or taking this kind of skew gradient of the corresponding stream function for complex potentials. And it turns out that any analytic complex function, z squared, z cubed, z to the fourth, any polynomial in z, cosine of z, sine of z, e to the z, log of z away from the origin, will establish these analytic functions, these harmonic real part and imaginary part that are solutions of Laplace's equation. And so these will give you potential or stream functions that can be used to derive these vector fields. So this gives you an entire infinite family of vector fields that satisfies these properties from these simple complex functions. Really, really useful. And in fact, these are the building blocks that for decades people used to design aircraft wings. So if you want to design a wing so that you get the right flow kind of over the wing, and it has the right lift and drag properties that you want, you can essentially create these potential flows using these analytic functions as building blocks to kind of build up the features of the flow and the wing that you want for design. That's what people did before computers, and it's pretty remarkable. All right, thank you.